Hey everybody, here we are again. So we've been talking about vertical datums and just in a general sense what they are. We haven't really worked with them that much, but now we're going to look at kind of how they're used to incorporate surface elevations along with ellipsoid elevations, geoid separations, and a geoid height. As we've discussed previously, the key basis for vertical datums is the geoid. So the geoid, before we get into what exactly it is, let's revisit a little bit of physics. So the geoid, of course, is a gravitational surface. So if we look at gravity itself, the force of gravity, we'll call it F, is equal to the gravitational constant, which is, I'll write it over here, it's 6.6743 times 10 g equals to the negative 11th. And the units are kind of funky. It's newtons meter squared over kilogram squared. But we don't need to worry about that right now. It's just the idea. So the gravitational constant is a constant throughout all of our experimentation, going back to the 1700s, back to Newton. We have measured gravity in several situations and found that there is this constant that relates masses and distances between the masses. So the force of gravity equals this constant times, if we have two bodies, the mass of body 1 times the mass of body 2 over the distance between 1 and 2 squared. So what we see is that the force of gravity is actually a function of the masses of two objects that are attracted to each other, and that force is inversely proportional to the distance between them. By inversely proportional, what I mean is as the distance between the objects gets larger, the denominator in our function here gets larger. Let me back up. As the distance between our two objects gets smaller, that is, they get closer together, we can see the denominator gets smaller, so our overall force increases. As two objects get closer together, the gravity between them gets larger. So let's see, I'll write that down. As objects get closer together, the magnitude or force of gravity, the magnitude of the force of gravity gets stronger. So keep that in mind as we go forward. So the geoid, if I have two objects, so let's say I have object 1 up here, call that 1, and we have some gigantic object down here, and this is object 2. And let's say that object 1 is falling, being attracted to object 2, so downward. Let's say when object 1 gets to this point right here, it has a certain force of gravity, force 1. And let's say that equals to 8.7 meters per second squared. Those are the units of force. And then we get down here, it drops down to here, and object 1, we'll say force 2 at this point it's going to be a larger magnitude, right? Because it's closer to object 2. And let's say here it's 9.72 meters per second squared. And it falls more, and down here it's at 9.72 I don't know, 9 meters per second squared, just making it up as I go. It's easy to note that anywhere in since the force of gravity is a function of the masses, but even more importantly, the distances between the masses, we can surmise that at each point, every single point, the force of gravity is growing. It's growing. I'm just going to say growing. So it's getting stronger and stronger. If I were to drop another object, say object 3, and when it gets down to here, it is object 3, we'll say the force equals that 9.72 meters per second squared. That's equal to this one here. So this one and at this point, they have the same magnitude of gravitational pull. I keep saying magnitude because their directions may not be the same. We can actually connect those, right? And if we were to have another object, say object 4 over here that has F equals 9.72 meters per second squared, we can connect those. And we're starting to see that we can develop a surface, right? We can develop a surface such that the magnitude of gravity is the same everywhere along the surface. And it would be a continuous surface, right? And that is the surface of the geoid. Now, since the geoid is a function of masses, then various centers of mass are going to affect the direction of gravity. And I will draw that out for you. So let's say we have a big mass over here and a big mass here, and we're dropping a ball from up here. So we're dropping a ball, we're dropping it down, and it's falling toward that surface of gravity, I'll call it, here's 1, here's 2. But as it goes down, then object 2 starts to influence the direction of gravity. So really gravity, if there are bodies of mass closer to the Earth's surface that are dense enough to affect that directional vector of gravity, what we have is a curve. Wherein the curve, and I didn't want you to turn. By the time it reaches the body of mass, if it reaches that body of mass where it hits, it's directly perpendicular to the direction of gravity. Now, what does that mean? Keep that in mind also. We're going to put these concepts together to get an idea of what's happening with the geoid. So the geoid itself is an undulating surface. Where did all my colors go? There we go. So let's say this is the surface of a geoid. So undulating geoid surface. This geoid surface at every point along I'll change colors so this is more obvious, every point on this surface, and I resisted calling this an imaginary surface, it's a theoretical surface, it's something that we can actually map and find empirically, and we can make predictions mathematically based on the geoid. But at every point on this surface, the force of gravity is the same. So this is called, let's say they're all 9.72 meters per second squared, and so on and so forth. And of course, I just picked these points randomly, but being a continuous curve, there's an infinite number of points along the curve, right? And at each of these points, the magnitude of gravity is the same, the direction is different, but the direction is always perpendicular to the surface of the geoid. And that's largely because, the Earth's crust is not a uniform density. There's iron deposits that are more dense than soft soil deposits or that sort of thing. So density is what really affects the direction of gravity. Now, if I were to drop a ball, it would make that curve. So if I were to extend, say, this one, if I were to extend that up, it would actually curve until the vector is nearly perpendicular to the center of mass of the Earth. Or, sorry, not perpendicular to, but it's nearly a direction that points directly to the center of mass of the Earth, the further away from the Earth I get. And then by the time it hits, of course, it hits perpendicular to the surface. And that is the concept that we use when we're leveling an instrument. We're looking at the bubble or the digital level. We're trying to find that perpendicularity with the local direction of the gravity vector. The fact that we use leveling techniques based on gravity renders it essential that we use a geoid for part of our height analysis. And we have a name for this geoid surface. It's called an equipotential, one word, I just made a capital there, but didn't mean to, gravitational surface. And this is the weird thing that I brought up last time is that everywhere on this sphere, or on this geoid, on this equipotential surface, equi and potential equal, equi meaning equal, potential meaning the same, or meaning the potential or the magnitude of the vector. Everywhere it's equally potential, so equal magnitude of gravity. So anyway, back to the weird thing. This looks like a surface such that water would pool up in that valley, but that is not the case because gravity is perpendicular to the surface everywhere. So what's weird is, is that this surface is level everywhere. Meaning that even though I guess we can think of the vertical aspect of the gravitational surface is undulating, the effect of gravity is level. So if I were to dump a bucket of water on this surface, or a truckload of water or whatever, the water would actually spread out perfectly evenly along the surface, right? It would be the same thickness everywhere because, gravity has the same magnitude everywhere on the surface. So that makes sense the more you think about it. So believe it or not, that gives us our third surface that we work with. So let me break that down. The first surface that we learn to work with is the surface of the Earth. So there's a mountain and a valley and another mountain and maybe a plateau. And then we have the ellipsoid. And the third surface is our equipotential gravitational surface, or the geoid. And there's no reason at all why they need to be drawn in this order. There's places on the Earth where the surface of the Earth falls below the geoid falls above the ellipsoid, and they interchange all the time because they're not. I guess the best way to put it is that neither the geoid nor the Earth's surface are even, and there isn't necessarily a relationship between the shape of the geoid and the shape of the Earth with mountains and valleys. They can interchange based on the density of the Earth, and the ellipsoid could be down here instead, or it could be up here. The geoid could be up here and fall down here. So keep that in mind when you're looking at the height calculations and working with orthometric heights versus ellipsoid heights, geoid separation, which is the next thing we're going to talk about. So the relationship between these surfaces. Let's keep it simple. I have a mountain. And let's say I have an ellipsoid. Oh, that's the wrong color. I want to stick with the same colors so I can make this as clear as possible. It's not that complex, but and then I have the ellipsoid surface, which is smooth, and I have the geoid surface, which undulates, right? And let's say I have a point here. Then the ellipsoid height is the height that is, I'll use that one, that is perpendicular to the ellipsoid. So that line, I'm going to draw it over here. That line is perpendicular to the ellipsoid. And so that is called the ellipsoid height, which is h. So h equals ellipsoid height. The other height we have is the geoid separation. So here I can say, how do I want to do this? This isn't quite... Let's do it this way. Let me take a new color. And remember I was saying when we drop that ball, it tends to attract to some body of mass that it becomes close to, that may have an effect that overrides to some extent the center of mass of the Earth. So let's say that curve goes like this toward the ellipsoid, and then it starts to veer off and hits the geoid here where it's perpendicular to the geoid. Okay, so two different lines here. So that is the orthometric height. So we'll say h. So h equals the Helmert orthometric height, which we just call orthometric height. We almost never throw the Helmert in there, but it is technically called the Helmert orthometric height. From this, we can see that there's a relationship between the ellipsoid height and the orthometric height, which is this distance here. We call that distance n. So n is the geoid separation, or you'll also hear it referred to as the geoid height, which is it's kind of a squishy term. I like geoid separation better because it tells me that we're looking at the separation between the geoid and the ellipsoid. So geoid separation or geoid height. And I'll just label these. This is, so I'll say P is point on terrain. Right there. Now n, the geoid separation is actually a vector. It's positive or negative, and how you think about that, how I think about it without forgetting, is that n is a geoid separation, so it's the separation from the ellipsoid to the geoid, and the direction is where the vector needs to go to get to the geoid from the ellipsoid. So in this case, n would be negative, right there. So we see that from that, we can see that h, big H, equals h minus n. Since n is negative, we're actually adding a value, and we get a larger value. If the geoid were above the ellipsoid, then n would be positive, and let's say that the geoid is, let's say for a second that the geoid is about here, then this would be n here. And our we would have h equals h minus n, and is positive, so this would become our geoid height, or not our geoid height, our orthometric height, h here, if that were the case. So h equals h minus n, and just shuffling around terms we use a lot, little h equals, or sorry, yeah, little h equals about, I'm gonna make these squiggly lines because they're not exactly the same, since we have that curve in the gravity vector. So approximately equal to h plus n, capital H plus n. So these two are ones you want to know. These are what we'll use for looking at ellipsoid heights, geoid separation, and orthometric heights. So big H approximately equal to little h minus n, little h approximately equal to big H plus n. And I should probably label my surfaces. So I have, this is terrain, this is ellipsoid, and this is the geoid. Geoid separation is negative in this case. So in the lower 48, so I'll say the contiguous 48, contiguous United States. In the contiguous United States, the geoid is below the ellipsoid, which is why I drew that diagram the way I did. In Alaska and parts of Canada, Canada, the geoid is above the ellipsoid. And to be honest, I'm not sure what the relationship of the geoid to ellipsoid is in places like Mexico, Central America, Hawaii, Guam. I'm not sure what models are used or whether the ellipsoid is above or below the geoid. But we're gonna mainly be working in the contiguous United States, where the geoid is below the ellipsoid, so that separation has a negative value, right? So as a convention, we say that the geoid separation is negative when below the ellipsoid, and it's positive when above the ellipsoid. And we can draw the conclusion, but it's also the case that n is 0 when, I'll move this up, at the ellipsoid. And just to illustrate that, pictures are good, right? I like pictures. Let's say we have some ellipsoid and we have some geoid that comes like this, undulates, that comes up above and below. Here, so here n is negative. Here, right at the meeting of the surface, n equals 0. Up here, n is positive, and here again, n equals 0, and down here, n would be negative. Then, as long as we know where that geoid separation is, then we know the value or the direction of n, the sign of n. Usually, what we're given from Opus Sheets, or I think Opus Sheets gives all the information, but typically when we're given geoid information, we're given geoid separation, and then the actual geoid, the orthometric height, is calculated from the geoid separation. We're not usually given the geoid height and then calculating the geoid separation. So geoid separation is important. So let's go back to looking at all three of the surfaces together. A little bit more terminology. So let's see, what did we have? We had the surface. So here's a surface and a mountain, and that's the terrain. And then we have the ellipsoid. And finally, we have the geoid. And let's say we have some point P up here, P, and we have our, let's see, I'm going to use that color. We have our ellipsoid height here. And remember, we have the, use the same colors. And then we have this curved line for the gravity vector. It should be a smooth line, sorry. Which is perpendicular by the time it reaches that equipotential surface. And if this curve continues upward, it would eventually become a straight line. Well, it's a curve, right? So it's going to have a tangent. If we were to draw the tangent between, no, that's not a very good tangent. I'm going to make this obvious. Okay. Oh, drawing. There we go. Well, I'm still not drawing it very well, but Need a new color. I don't know how that'll show up. I haven't used this yet. But we can draw a tangent line to that curve at that point, right? So let's say that's the tangent line at the point. And then we can also extend our ellipsoid height up. And we have this angle here, don't we? An angle between the tangent to the gravitational vector and the extension of the ellipsoid height. That is called deflection of the vertical. And this is what causes, well, amongst other things, but this is something that causes misclosures in level loops. Because what we're doing is we're taking a 90-degree angle from our level line, and if we think about how that looks, so we have our level line here that is perpendicular to the gravity constant, or the gravity vector. But really what we need to be doing is accounting, much like we do in convergence, but we would need to account for this distance here, this angle. We would have to account for that angle. So what we're really getting when we are measuring a perfect horizontal, what happens is the deflection of the vertical causes the horizontal to be off of our horizon. So this is our horizon. This would be our horizontal line that we create, and the angle between them is the same. It's still that deflection of the vertical. So that's deflection of the vertical. I should probably write a definition. Deflection of the vertical. And by the way, this green line I keep drawing for the gravity vector, I keep calling it the gravity vector, it's called a plumb line. And we've all used, or we should all have used plumb bobs before, right? We drop a plumb bob, and that's how we find vertical. Well, in reality, that plumb line, that string, has a bit of a curve to it. Nothing we would ever see or even detect on the distance between the top of an instrument and the ground, but there is a curve, and if that plumb line were to continue, it would actually curve more and more. So we would see that if we were to hang a string with a plumb bob on it. So plumb line. So then deflection of the vertical is, as a definition, the angle between, come on, change colors. The angle between the local direction of gravity or plumb line and the ellipsoid normal, or the line from the point perpendicular to the ellipsoid, so the ellipsoid normal. That is deflection of the vertical. I'll just put as a note, this causes error in level loop closure. Cool. I think we have all the tools to start looking at datum conversions. That was a lot of definitional stuff, pictures, but now we're starting to get what we need to talk about conversions. So we're going to go in reverse order. I'm going to first talk about vertical datum conversion, and then later I'll talk about horizontal datum conversion. So vertical datum conversion. So like before, I have mentioned two vertical datums that are widely in use. We have NVD 29 and NAVD 88. Used a lot. And we may want to convert from that NVD 29 to 88 to modernize, sort of modernize our heights. Or we may want to go back. We may want to take one of our surveys and compare it to heights of an older survey. So we may want to convert our data to NVD 29. So we need a way to convert back and forth. And we have several methods. So these are all NGS used methods. The first one is to reobserve. So that what that means is we have a survey from, say, 1940 that gives heights in NVD 29. However, our project is in NAVD 88. We can go out, find the monuments, reobserve them, but then calculate them in NAVD 88 and just disregard the NVD 29. So we are converting NVD 29 elevations to NAVD 88, but we're not using any sort of computational methods. We're just reobserving. We're actually physically going out, starting with a benchmark, a physical height with an elevation in NAVD 88, and then we're level looping between all of our points of our network and getting them all in the same vertical reference. So that's reobserving it. It's the best method in terms of getting a reliable product at the end. However, it's expensive in time and money, which are kind of the same thing, right? They're synonymous. Not really synonymous, but time is money. So time and money, expensive. So it's not done all the time. On smaller projects it'll be done, but we have a really large project in which we need to incorporate tons of elevations. We need something better. So there's also the idea of datum correctors. So we might just observe a couple of the points, maybe 3 or 4 points in our new system, and then just come up with the difference between the numbers in one vertical datum, and just add the difference to all the other points that we got from the difference. So then all of the points in our network, without observing them, we're just stealing them from a prior survey. We can get valid elevations on. So this uses the original least squares adjustment, LSA, parameters. So it takes all of the parameters from the original least squares adjustment, and we just put in some of our difference values, and then recalculate the least squares adjustment, and it'll spit out the new elevations. So This is an approximation. In fact, I'm pretty sure everything except reobserving is an approximation. Reobserving would be exact within a margin of error, right? However, using datum correctors wasn't practical because until recently, least squares adjustments, the concept of least squares adjustment was not readily available. Well, I'm getting over my face. I don't want to lose you here. Was not readily available to the private sector. We start to see that change in the 80s because the private sector, computers are becoming democratized. And what that means is more ubiquitous in use. More people, computers were coming down in price. We no longer needed to have entire rooms dedicated to supercomputers that are refrigerated and all that. We're starting to see desktop computers pop up in firms and that kind of thing, and eventually in homes. To the private, I should probably finish my sentence. I get to talking and I forget to write at the same time. So to the private sector. All right. So 3, the third one, let me scoot this back over a little bit, get my 2. So 3 is called the average bias shift. And this is one that we're going to work with. One of them that we're going to work with. So average bias shift is where you take a sample of points and you measure the elevation difference between one datum, the elevation in one datum and the elevation in the other datum of each of the points. You average out those distances and then you apply that average to all of the other points in your network. So average bias shift. It works well where the geoid is smooth, so not a lot of undulation. I'll put in quotes smooth because it's always smooth, but smooth meaning more like an ellipsoid. It's a not a lot of undulation. Or for small areas, small project areas. And we apply an average distance value, vertical distance value, from one, or I'll say in one datum, in one datum to get elevations in another datum. So average bias shift. Scoot that up there because I probably wrote over my face again. Sorry about that. I forget that it's there. Not my face, the picture of my face. Let's see, 4. Fourth method that NGS uses for vertical datum shifts. We readjust original observations, and by readjust we mean a least squares adjustment. So we're not maintaining any of the parameters from the old adjustment or anything like that. We're coming with a completely new adjustment, and we're throwing the old observations into a new adjustment that would bring our heights up to the desired datum. The problem with that is that think about some of the elevation, say, flood surveys, floodplain surveys done in, say, the 30s or the 40s. Those field notes aren't available. So the problem we have is that the data is not always available, or hard to find. Also, the observations might be too old. The instruments they used wouldn't meet the standards of today. So observations too old. And let's see, another one. The observations may be otherwise inaccurate. Either from systematic errors that weren't processed out, or again, equipment that wasn't as precise or accurate as we have now. So technological advances, observations may be inaccurate. So, number 4 and number 5. So that was readjusting original observations. We're not going to do that. So, but it's good to know that that is a method that NGS does sometimes use. So 5, the VertCon program, or now it's NADCon. So NADCon, which is an NGS tool. If I say VertCon, just know I mean NADCon. NADCon is, so NGS, the NGS toolkit has been revised to NADCon, wherein they've kind of consolidated a lot of the tools that were offered in the NGS toolkit. One of those being VertCon, which is a vertical converter. Now we have NADCon, which does horizontal, vertical. You just pick what kind of conversion you want. So NGS tool NADCon. With that, you need to know a little bit about your datum. You need to know, in what system, what horizontal system the survey was made, and the vertical datum it was in. You might need to know, like, for instance, what epoch the International Terrestrial Reference Frame coordinates are in, so that you can properly convert them. You have to know a lot more things to perform this conversion. So it's not always practical. So this is a nationwide NGS surface fit. So NGS nationwide surface fit. So they actually went out and gathered empirical data to build that conversion. Let's see, the latitude and longitude. So phi and lambda give us a datum shift estimate. That's how that works. And also you can convert Earth-centered, Earth-fixed (XYZ) coordinates this way also in the NGS tool. The uncertainty or standard deviations is about plus or minus 0.02 meters or 2 centimeters. So not good for, I should say not, it's good, it's not sufficient. For survey work. I'll put survey engineering work. But it is good enough for mapping. Good for mapping. Or recreation grade. We haven't used that term yet. Recreation grade projects. I wish you guys could yell at me when I write over my face, but I can't hear you. So, and so for mapping or recreation grade is what that's the primary use of this tool, is for mapping. Okay, and then that leads us to number 6, which we will be working with. The 6th and final NGS conversion method for converting vertical datums. It's called the two-plane method. Two-plane method. Or inclined plane method. You'll hear sometimes. They're the same thing. And this one is the best for surveying. I'll say survey accuracy. And application. So engineering application. And what else can we say about the two-plane method? Each datum is treated as a plane, which is nice because we can adjust things on the plane because it's Euclidean surface. Planes are Euclidean surfaces. The good old fifth postulate applies. Parallel lines stay parallel. Let's see. In a nutshell, how it works is that it applies an east, west, and a north-south rotation and datum shift. Or datum shift we could think of also as a translation. Right? We can perform, in fact we do perform, a least squares adjustment. And I do realize, I think I said it before, I do realize that most of the course, so least squares, adjustment for least squares is not a prerequisite to this course. So my assumption is that none of you know anything about least squares. I know some of you have taken it, but I'm going to treat this as though none of you have taken least squares. Just to keep an even playing field. So can perform a least squares adjustment incorporating how do I want to say this? Can perform LSA incorporating predicted residuals and extracting actual residuals. And if this is Greek to you and you don't speak Greek, don't worry about it. This is to give you some exposure to the terminology. Residuals, just like we talk about in statistics, right? The difference between an observed value and the most probable value is a residual. So, extracting actual residuals. So the datum shift looks like, whoops, or I'll just say equals because it does. Our total datum shift looks like or equals alpha E. So this rotational angle in the easting times some northing minus our ideal northing plus, so this ideal northing is like an average value. It's our most probable northing. So an observed northing or a calculated northing of an actual point minus some average northing plus the rotation of the northing axis. Better write that better. I hope you guys forgive me for all these scribbles and stuff. I keep saying, but I'll keep saying it anyway. It's really hard to write on this thing. So the rotation about the northing axis times the easting of some point minus an average easting value plus some translation in the up direction. So that T sub z is just a translation vector for the datum translation. So where N naught and E naught is the centroid, which we get by an average, is the centroid coordinate. And this should look familiar in a diagram. It kind of looks like we have here's our, I don't want to put it there. So let's make it central. So here's our N naught, E naught, and we want to translate and rotate to get up to some northing and easting of a point. Our new centroid of our area. So that's all the concept of datum shift. We're going to next time take a look at the average bias shift method and the and this method. I already forgot what it's called. The datum shift, or the two-plane method. So we're gonna look at the average bias shift and the two-plane method and compare the results and see what it looks like. We'll do an example once I walk through the process. Okay. Anyway, next time we get back to some computational things. Hope this finds you well, and have a great day.